Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today's discussion is going to be a second bit of the concept of entropy change for an ideal gas. And in our first discussion, we had mentioned the concept of entropy insofar as an ideal gas is concerned. And we had given different representations, especially from the first, of course, concept of the first law of thermodynamics, whereby we see that we can be able to represent this particular change in entropy using this derivative of this specific equation, whereby we see that this is going to be represented as the sigma q reversible is equivalent to Cv dt plus Pd. And we have said that we can be able to, of course, give the change in entropy using this specific part of the equation which we are given as the energy, which is sigma q reversible, by dividing it with, of course, T. We have mentioned that, of course, this specific aspect of entropy is the change in heat over absolute temperature, and therefore this was given in terms of a ratio of sigma q reversible over T. And therefore, for us to find this specific change in entropy from this first equation, we're going to do a division of this specific equation by T. But from this particular case, we have decided that if we try to consider an ideal gas, then we're going to have it using, so I'm just going to maintain this one. Let's just have this one as Q reversible over T, which is going to represent the change in entropy. So we said that from this one, we can be able to represent the pressure using the ideal gas equation, which was PV equals nRT. Now for a single mole, then therefore this is going to imply that we can be able to have pressure given as RT over V given as such. So therefore we can be able to have a second version of this specific equation using this particular representation for pressure from the ideal gas, whereby we're going to have it at sigma Q reversible is equivalent to Cv dt plus. Now the pressure which I've said is going to be represented using RT over V. So therefore we're going to have RT over V dV. So this is a substitution for pressure, then therefore this is going to have a second bit over this specific equation given as such. So for us to obtain this specific representation for entropy, we're going to do a division over T over this equation, and therefore this is going to be, so this, just for it to be elaborate, I'm going to have it times 1 over T given as such. So for the last bit of the equation, then therefore this is going to be, of course, cancelling out with this. So therefore we're going to have it given as R over V d RT dVt given as such. So therefore we're going to remain with the concept of dV over V given as such, with R being a constant. So for us to obtain therefore the ds from this specific representation, we say that we can be able to give an integral form of this particular equation, last equation that we have, whereby the change in entropy is given as S2 minus S1, which is of course going to be equivalent to the integral between T1 and T2 over this specific Cv dV plus the integral between V1 and V2. So this second bit is going to involve the change, this is the change in temperature, and this is the change in volume. dt over T is going to be the change in temperature, dV over V is going to be the change in volume. So therefore that is going to be involving dV over V given as such, whereby R is going to be a constant, so therefore I'm going to take it out. So we can as well have a version of this specific equation, whereby we're going to have it being given as, so this first bit of it then therefore was to be Cv dt 1 over T given as such. So therefore we can be able to have this particular version of the equation being represented, whereby we're going to have it given as, so Cv, which is molar heat capacity at constant volume, is going to be taken out so that we can be able to represent this one as T2, and then we're going to have dt over T given as such, and then R, the integral between V1, V2, dV over V given as such. So this is going to give us the delta S, which is going to be representing the change in entropy. And therefore, finally, this is going to give us a representation of a delta S given as Cv at the natural log over T2 minus T1 over T1 plus R the natural log over V2 over V1 given as such. So this is what we said was a representation of this specific aspect of entropy, and therefore we had said that we can be able to consider from the ideal gas equation this specific change in entropy, whereby we're going to take the initial and the final temperatures being particular variables which are going to take place in this specific condition as we have just given as such. And therefore, we give various variations of this specific formula, especially if we had considered the case of an ideal gas equation, whereby for pressure 1, volume 1, we can be able to represent R in this particular case, whereby pressure 1, volume 1 over T1 is going to be giving us a constant, which is going to be R. So we can be able to have this version of the equation, whereby we're going to have P1 V1 is equals R T1, and P2 V2 is equivalent to R T2 given as such. So from these specific two equations, we can be able to have a representation of the ratio of volumes, whereby we're going to have V2 over V1 being represented using P1 T2 over P2 T1 given as such. So that one shows the inverse proportionality of these two specific aspects of pressure and of course temperature, whereby we're going to have it, or this particular second aspect of the equation. We can see this is the volume 2 over V1 is equivalent to P2, P1, P2, T2, T1, and of course we can be able to have a different version of the change in enthalpy from this specific variation, or just by doing a substitution in this particular equation for V1, V2, then therefore we're going to have a different version of that specific equation. Now we said that there's a relationship that is going to be experienced between the molar heat capacity at constant volume and the constant of course pressure, where we will say that we can be able to represent them using Cp and Cp respectively. So there is this specific let's have this representation for the last equation we had said for enthalpy Cv, the natural log over T2 over T1, and then plus R, the natural log over V2 over V1. But we have said that V2 over V1 is equivalent to P1 T2 over P2 T1. So therefore we can be able to do a substitution of this one and then have a version of this given as Cv, the natural log over T2 over T1, plus R, the natural log over P1 T2 all over P2 T1. And from there, what we refer to as logarithms, we can be able to split this part, second bit of the equation, therefore giving us the natural log over T2 over T1 plus R, the natural log over P1. Let's have this one given us a T2 over T1 for this second bit. So for us to have this second bit of pressure, we can be able to just do an inverse of this. So this is going to give us a negative sign for R, the natural log over pressure 2 over pressure 1. So basically the second aspect of it is a split of this combined equation for this. So this is going to give us this one from logarithms. And therefore we can be able to maintain them as such. And we would say that there's a relationship that is going to be existing between this Cp plus R, which is going to be equivalent to Cp. So we can be able to consider this one at constant pressure, a constant volume and temperature, this specific version of the equation. And we said that if we have T2 equivalent to T1, this is going to imply that the change in entropy at constant temperature then therefore can be given in terms of R, the natural log over V2 over V1, of course, which is going to involve only volume and pressure, and then we're going to have this one also equivalent to R, So this is going to be negative R, the natural log over P2 over P1 given as such. So we can be able to represent a change in entropy at constant pressure using these two specific versions of the equation using the volume and the pressure. And therefore this is going to be referred to as isothermic or isothermal change insofar as entropy is concerned. The next we're going to see that we can be able as well to describe this one using a constant pressure, whereby if P1 is equivalent to P2, we're going to have the change in entropy at a constant pressure, whereby, so this is going to be a condition where P2 is equivalent to P1, and therefore this is going to be represented in terms of a Cp, the natural log over T2 over T1 given as such, whereby this particular processes of a constant pressure is going to be, so therefore we're going to we're not going to have this specific element, so we're going to have this one referred to as an isobaric process given as such. So the isothermal process for the constant temperature T1 is equivalent to T2. The second case is a constant pressure, whereby we're going to have it represented as a delta S subscript P is equivalent to Cp natural log over T2 over T1. And then lastly, we're going to see the case of a constant volume, whereby V1 is going to be equivalent to V2. So whenever V1 is equivalent to V2, then the change in entropy at constant pressure is going to be given in terms of a Cp, the natural log over T2 over T1. So this basically is going to be a consideration of this general representation, whereby we're going to have either pressure, temperature, or volume in this particular case. So if we do a substitution for V1 is equivalent to V2, this is going only to remain with this one under constant volume, of course, which is a Cv, which is a version of this. So if we have a constant, perhaps constant pressure, then therefore we're going to represent this one, which is an isobaric, or rather, which is going to be an isobaric process. Then we're going to also to have only the Cp being represented from this specific relationship, whereby we said it's going to be Cp natural log over T1 over T2. And of course, lastly, we had said that if we have a constant temperature, then therefore we're going to have this specific portion of the equation being not considered, whereby we're going to consider this specific aspect of volume. And that is going to give us a summary of the various relationship that is going to exist for isothermic or isobaric or isochoric changes insofar as enthalpy change for an ideal gas is concerned. So I hope that is comprehensive. Catch us in our next videos. We're going to do various aspects of evaluation of some basic examples which are going to assist us comprehend this specific aspect. So that is it for now, guys. Bye. God bless you.